So in this section, we're going to talk a little bit about the sun and how it generates its power and how we know. So the sun generates an incredible amount of energy. We'll talk about how much that is exactly, and has continued to do so for billions of years. These are pictures of Lord Kelvin and Hermann von Helmholtz. They were both prominent scientists. Helmholtz was a German, a polymath. He was active in all kinds of subjects: math, physics, chemistry, physiology, psychology. Lord Kelvin was an English physicist who was really sort of one of the senior English scientists. You can see he lived a very long time. What is that, 83 or something like that? And so he was a very important scientist in England. He did a lot of his work in thermodynamics, but in a lot of fields. He was involved in the first transatlantic cable that got laid from, I forget, the west coast of maybe Ireland and over to Nova Scotia or something like that. So that happened during his lifetime, and he contributed to it. He finally got it to work, I believe. So the question became important in scientific circles as to how old the Earth is. In the 1800s, geologists like Charles Lyell and evolutionary biologists like Alfred Wallace and Charles Darwin began to argue for an ancient Earth. The geologists, because they just saw enormous layers of sedimentation in cliffs and knew that the rate of sedimentation was extremely slow. And they were trying to reconcile those two things. And then the biologists were mostly from evidence from evolution, fossil evidence, and things like that. James Hutton wrote a book in the late 1700s called The Theory of the Earth, in which he said, where's the effect of no prospect of a beginning and no prospect of an end, or something like that. He was arguing that the Earth was much older than people thought it was. So their arguments were based on sedimentation rates and fossil records and stuff like that. William Thomson, I wrote his hip-hop name was Lord Kelvin. The Lord Kelvin you saw on the last page, argued there is no power source that could power the sun for such a long time. And so he said the Earth can't possibly be that old because the sun isn't that old. And there's nothing that could power the sun for that much time. In fact, he argued that if you made it out of the most energetic fuel we have, which is like oil or something, it wouldn't get anywhere near a billion years. And then, so he, along with Hermann von Helmholtz, studied a little further and decided that, well, if you allowed for gravitational collapse of the sun, so in other words, as the sun forms and all that material falls inward gravitationally, that has energy too, and actually a lot more energy than just making it out of oil would. And so they could make it as old as 20 million years, but they could argue that the sun could last 20 million years, but nowhere near billions. And so they were, Kelvin especially had the courage of his convictions, and he fought against claims for an ancient Earth, and even in print, and like newspapers, he would argue that these things shouldn't be printed in the London Times and stuff. He would make those arguments. Darwin, however, was a smart guy too, and he said, look, we know it's this old. Physicists simply haven't found out what's producing the energy, and they need to work harder, and it wasn't the job of biologists to solve that problem. Kelvin was arguing that no information should be published talking about ancient Earths until somebody has figured out how it could happen. And then in the late 1800s, a physicist named Henry Becquerel first discovered radioactivity. People after him, like Marie Curie and Einstein, and other people, began to understand that there were processes inside atoms that we hadn't quite understood yet. These were processes that ultimately were found out to involve the nucleus of the atom. Nuclear reactions involve the nucleus of the atom, and they're different from chemical reactions. Nuclear reactions are typically around 1 million times more energetic per reaction than chemical reactions. This means, for example, that a small amount of nuclear fuel, maybe 10 pounds, could produce the same amount of energy as a trainload of coal. This is one of the big advantages of nuclear fuel. Up to this point, all human energy sources involved only chemical reactions. Those are things like burning wood or oil or other fossil fuels, those types of things. So anytime you see a fire, That's a combustion process, and that's a chemical reaction. The sun is not actually on fire. It's radiating light due to its temperature, not due to chemical changes, which I won't go into too much. We talked a little bit about that in the chemistry section. So suddenly, with the discovery in the early 1900s of nuclear reactions, there was a way for the sun to have been radiating energy for billions of years. This is the first clue. So this is a picture of Albert Einstein in formulating the equation E equals mc squared. Einstein showed that tiny amounts of mass can be converted into enormous quantities of energy. This is one of the most important principles in understanding how stars are powered, stars like the sun. Another important character in this, and there are many that aren't included here, is Wolfgang Pauli. He was an Austrian. He predicted the existence of the neutrino, a tiny particle that's the byproduct of nuclear fusion reactions that power the sun. These little neutrinos became central in understanding what happens inside the sun, because the reactions that occur inside the sun, the nuclear processes, don't get out. They stay inside the sun. All we see is the energy that takes maybe 1 million years actually to work its way from the core to the surface of the sun and then come off as heat. But these little neutrinos, they can run through the sun like a mouse through a chain link fence. They just get right out. And so the scientists were able to ultimately, Pauli didn't know this at the time, but were ultimately able to use these neutrinos to let them understand what was happening inside the sun. So if we talk about nuclear power, there are two basic types. One is fusion. That's where you're putting things together, like in picture A here. And one is fission, where you're breaking things up. And so if you want to use these to create energy, you can either take small nuclei and combine them, or large nuclei and split them. When you get to middle-sized nuclei, you can't do much with them. Iron is kind of right in the middle as far as that's concerned. So the fission process is produced by breaking up big nuclei. The fusion process is combining little nuclei. Both of those processes produce energy as well as that combination. So in nuclear fusion, two smaller nuclei are combined to make a larger nucleus, not necessarily large, like two hydrogens will make a helium. This process releases energy. Since the nuclei by themselves, without the electrons attached, repel one another, so the nucleus of a hydrogen atom is just a proton. And so if you want to combine two protons, well, like charges repel, they repel each other. And so the only way to combine them is to get them going really fast. And the way that happens inside the sun is very high temperature and pressure. So this process is only energy producing for nuclei smaller than the nucleus of an iron atom. Nuclear fission is the breaking up of a larger nucleus into a smaller nuclei, also with the release of energy. Nuclear fission only releases energy when carried out on certain nuclei larger than an iron nucleus. So we now understand the process that goes on in the sun, and so there are 3 steps to it, and I'm just going to walk you through them. The sun is mostly hydrogen, as are all stars. In fact, the universe is 70% hydrogen, 75% hydrogen by mass, something like that, and 90% by atoms, if that makes sense. When you're fusing hydrogen to helium, it goes like this. There's a proton-proton chain. Notice we've pitched off the electrons here. It doesn't really matter. The electrons don't participate in this. The temperatures are so high, the electrons aren't even on the nucleus anymore. So in the first step, 2 hydrogen nuclei, 2 protons combine to form a single nucleus. This is called deuterium. And then 2 things come off, a neutrino, which comes into the story later on, and a positron. And so if you look at this red guy, the blue guy is a proton, the red guy is a neutron, and it's like the positive charge of the proton got pulled off and sent off with this positron, and what's left behind sort of is a neutron. That's not quite right, but you can think about it that way. The total positive charge is the same. One of the positive charges is here, one of the positive charges is here, and so now we have a proton and a neutron here. And these 2 guys still make a hydrogen atom because there's only 1 proton. If you remember the atomic number, which is the number of protons, tells you what flavor atom it is. And 1 proton means you're a hydrogen atom. It's a different isotope because there's a different number of neutrons. This has 1 neutron, whereas these two guys have 0 neutrons. So this guy is called deuterium. So then, in step 2, that deuterium atom, nucleus, which just happened to occur somewhere inside the sun, runs into another proton. And these two guys combined. Again, these are just random reactions, but the stuff is very compressed, and it's moving it. It's got very high temperature, so it's got a high velocity. And so, in this case, one hydrogen nucleus here, which is a proton shown in blue, combines with the deuterium nucleus from the previous step. That's this guy. The product is an isotope of helium. It's got 2 protons, that makes it a helium, plus a neutron, so it's a helium-3, because you remember this term here is the number of nucleons, the number of protons plus the number of neutrons, and that's 3. And so now we've finally got a helium. So we've combined 2 hydrogens, 2 protons to make a deuterium, and then a deuterium and a proton to make a helium nucleus, right? With a helium, we call this a helium-3. The normal isotope of helium is helium-4. It's got 2 protons and 2 neutrons. So step 3 takes 2 of those helium-3 nuclei, these 2 guys, and combines them, and you get a helium-4. This is the stable isotope of helium. And then if you want to do the accounting on this, 2 blue guys have to come off, and so here 2 hydrogens given back, and now we've created a helium nucleus from the hydrogens that we started with. And these guys just run back and start the process over again. And so it's by this process that the sun is slowly converting hydrogen into helium and emitting energy while it's doing this. The sun uses the above process to convert about 600 million tons of hydrogen to 596 million tons of helium. And then the difference between those, which is 4 million tons of mass, is just converted into energy using Einstein's formula, E equals mc squared. We can just plug all that in because a metric ton is 1,000 kilograms. And so 4 million times 1,000 is 4 billion. That's how much mass is converted into energy. By the way, it's all kind of in the form of gamma rays and X-rays and a little bit of kinetic energy, but it doesn't matter. That's how many kilograms of mass is converted into energy every second in the sun. Since we know that the speed of light, c, is 300 million meters per second, we can use E equals mc squared and multiply all that out. You don't have to do it if you don't want. You get 3.6 times 10 to the 26 joules each second. If you count up all the zeros, that should be right. So it's 3, 6, 9, 12, 15, 18, 21, 24, 25 zeros, and then a 36 in front of it, so it looks right. And so this means the sun is running at about 3.6 times 10 to the 26 watts. This is a rough number. I just use round numbers here. I think in the last section we said it was 3.8, but it doesn't matter. It's in the vicinity of 3 point something, close to 4 times 10 to the 26 watts. This is the rate at which sun is producing energy through this process. And it's measurable. We can sort of measure and see that we're pretty close. So if we back up a little bit and talk about how these processes work on Earth, it's a little different. Let me just take a side step and talk about nuclear power on Earth for a minute. Nuclear reactors created by man are all based on fission. Large nuclei are broken up into smaller ones, and in the process, energy is released. For example, a neutron, so a typical nuclear reactor will do something like this. Let me edit this real quick. So nuclear reactors created by man are all based on fission. This is where large nuclei are broken up into smaller ones. And you can see an example. So we take a uranium-92. Uranium has atomic number 92. The isotope is 235. This is a big atom, right? And we're going to split it. And so you fire a neutron at it. That's what the 10N is. Again, the top number is the atomic weight. The bottom number is the atomic number. That's how many protons. Clearly, a neutron alone has no protons, so it's a 0 there. So you hit this into a uranium-235 isotope. and it splits, for example, into this isotope of barium and this isotope of krypton, and then 3 more neutrons, and then a bunch of energy comes out. And so this is how some of our nuclear reactors work. The 10N is a neutron, the 1 is the atomic mass, and the 0 is the atomic number. The 235 is the uranium isotope. It's the 235 isotope of uranium. All uranium atoms have 92 protons. That's what it takes to make uranium. So this isotope then has 143 neutrons, but there are isotopes that have different numbers. The most common isotope of uranium is 238, so it have 146 neutrons. And then if you look on the right of that equation, you notice that what's left, along with the energy, which is what you were after, right? What's left is this barium and this krypton. It turns out these are 2 very radioactive isotopes. They are the radioactive waste of nuclear power plants, and this is the stuff that you don't want in your water or in your food. And so when you run these nuclear reactors, you have to find a way to dispose of this stuff. And sometimes you'll hear politicians talking about it, how to dispose of nuclear waste. And it's a problem around the world. But it's not just a problem for nuclear reactors. All kinds of energy sources produce pollution. And so we have to find the best solution for all of these things. So what's left is this, and these are unpleasant things to deal with, the barium and the krypton. The residue, the byproducts of nuclear fission create a problem. And so because of the byproducts of fission reactors are dangerous to humans, disposing of the waste is problematic and sometimes costly. Before we dismiss nuclear power and just say, hey, we can't use it, let's remember that the byproducts of fossil fuels, fuel combustion on Earth, also creates health concerns. Particularly coal is a nasty pollutant. These concerns are not just about climate, but also for respiratory issues people have in large cities where there are power plants nearby. The good part about nuclear power plants is that when they're working correctly, all the waste is contained in the plant. You're not blowing it out into the air. It's just, as long as you don't have leaks or meltdowns or anything like that. And this is as opposed to things like fossil fuel plants, which often are blowing them into the air, but not always. And of course, cars. Finally, it's good to remember that there's more nuclear fuel on the planet than all others combined. And so I'm not an advocate for any of them, but it's important to understand how they all work, right? What's the good and bad of all of them? So what's the advantage of nuclear fusion, right? We saw above the possible dangers of nuclear power we currently use. Well, unlike fission reactors, fusion reactors would just produce helium. It's an inert and harmless gas. We already saw the process that you can create it by. There'd be no dangerous byproducts. It's way more energetic per pound of fuel. Unlike fossil fuels and nuclear fuels, pretty much every country has access to water, which is all you need to get those hydrogen atoms. You just grab some water. The problem is that for the reaction to occur, it needs to be at about 27 million degrees. And there's no containers that'll do that for you. There's no container that you can cook up to 27 million degrees and have it not vaporize. And so for decades, scientists have been trying to come up with ways to contain a fusion reaction. And one possibility is contain it in a magnetic field. Oops. Let's see if I can get back to that. I'm lost forever. And so this is a sort of a model of a project that's being worked on by multiple countries. Fusion reactors have been worked on for more than 50 years, and slow progress is being made. But the idea is you, instead of having a metal container or something that holds this reaction at 27 million degrees, you have a magnetic field that traps the particles in it, and so they're floating in space inside this magnetic field, and then you get it to 27 million degrees, and then they're not cooking anything. They're just producing energy that you can capture. So the facility is being built. This facility is being built in France. Construction will require 10 million components and 2,000 workers. The date for the start of operations is yet to be determined, but it's the goal is to produce 500 megawatts of energy. This would be a huge boon to power around the world if we could do this, because it would clean up our energy use and make it much more accessible to to people all over the world. Renewables, of course, are also generally widely accessible. Okay, let's talk a little bit. Let's get back to the sun. So that was a little digression there on nuclear power. So I think we all have an experience of what pressure is. You have pressure inside a balloon. There's pressure in the atmosphere. Gas particles are in rapid motion, and as they bang on things in sort of their normal mode of moving, they produce pressure by hitting the walls of their container in very high rates. It turns out that happens in the sun as well. And the sun is at something we call hydrostatic equilibrium. The idea is gravity is kind of trying to crunch the star down. Gravity always wants to crunch things smaller, but there's an outward pressure that's the result of the fusion that's happening inside the core of the sun. And so those are balanced, and we have a hydrostatic equilibrium. There's an enormous inward gravitational force. There's an enormous outward pressure force, and those are competing. And the sun stays stable until almost all of its hydrogen is converted into helium. So this is a picture we saw in the previous section, and it just outlines the interior of the sun. Energy is generated in the core by fusion in the form of hydrogen into helium. This energy is transmitted outward by radiation, that is by the absorption and re-emission of photons. In the outermost layers, energy is transported upward by convection. And so that's what you're seeing here. Radiation is happening where these little arrows are, and these little loops are convection region. Even still, scientists estimate that it takes 100,000 to 1,000,000 years for the energy to get out. Energy is created today won't make it to the surface of the sun for a very long time. So here's some physical quantities in the sun, graft versus density. So let me just talk about some of these graphs. First of all, the horizontal axis on these things, the left side is the center of the sun, and the right side is the photosphere, or the surface of the sun, if you want to call it that. Right? So 0 to 1, that's 0 is the center, 1 is the quote-unquote surface of the photosphere. And so you can see that that at the center, the temperature is 15 million Kelvin, which is about 27 million Fahrenheit. And so that's what it is at the center. At the surface, if you remember, the surface of the sun is at 10,000 degrees Fahrenheit. So it's come way down by the time you get to the surface. Similarly, the density is 150 or 160 grams per cubic centimeter at the center. That's where it's most compressed, right? All the gravity is squishing the hardest there. At the surface, in the photosphere, it's like 10,000 times less dense than air. Where is the luminosity produced? Right, all of the energy for luminosity is produced within the first third of the sun's radius, so all in the core, even less than that, really. And another interesting thing is the percent of hydrogen by weight at different radii, right? In the solar system, the percent of hydrogen by weight is about 75%. If you just average over the whole solar system, which is basically just the sun. And so in the outer parts of the sun, in the radiation zone and the convection zone, there's about 75% hydrogen by mass. But in the interior, as you get closer to the core, more and more of the hydrogen has been converted into helium, and so the percent hydrogen steadily declines as you go to the center. So this is the percent of the total mass of the sun. More than half of the sun is within the first third of a radius, and certainly nearly all of it is within the first 6/10 of its radius. And so the core is way more important in terms of where the mass is than the outer regions of the sun. Helioseismology. So we talked about how we use seismology, or how geologists use seismology on the Earth. by looking at vibrations, we can kind of tell what's going on inside. It turns out you can do helioseismology also. New observational techniques permit astronomers to measure small differences in velocity of the sun's surface. So the sun's surface is oscillating up and down relative to the surfaces. So when we look at it, some parts of the surfaces are red shifted because they're moving away, and some are blue shifted because they're moving towards us. By studying those vibrations, astronomers can learn a lot about the interior of the sun, in the same way that geologists can learn a lot about the interior of the Earth by studying the vibrations. To understand how the interior of the sun worked, how the nuclear processes that we talked about required figuring out about neutrinos. When Pauly, who we talked about earlier, did his experiments, they were in like 1933. This is Raymond Davis. Pauly made the prediction that neutrinos would exist in 1933. This is Raymond Davis who did the first experiments looking for neutrinos, solar neutrinos. This is in the late 1950s. Let me just see if it says here. I think in the 1950s or 60s he did his first experiments on neutrinos, and they failed to match the results that would be predicted based on how we understood the nuclear processes happening in the sun. And it wasn't until recently, like in the last 15 years, like in the early 2000s, that new neutrino experiments finally showed that the neutrinos we see coming out of the sun are consistent with the nuclear reactions that we outlined above. This is the Sudbury detector, neutrino detector. This isn't a question. It says, while scientists have never been able to get fusion reactors to work, they can make very small numbers of fusion reactions happen using particle colliders. So we can simulate all of the reactions. We can create all of the steps in the sun's nuclear fusion process in laboratories using particle colliders. That's what that's saying. This process allows them to carry out each step of the hydrogen fusion process that they believe happens inside the core of the sun. While they cannot look for all the byproducts of the collisions because they can't see inside, they can detect these neutrinos, which can escape the sun easily. So the work on neutrino detection is what allows scientists to know that they understand what's going on inside the sun. That's it. So again, look to the PDF for questions, because I'll probably add some more.